Hi, it's Guy at Flying Pig Labs. I was going to show you real quick this CU320 communication block. The CU is the main controller for up to 6 drives, and also I/O modules. Like we actually have a little TM31. They have a whole series of I/O modules that can hang off the drive click. Um, so I was going to show uh, how to set up the little communication block. This is just one way, kind of a little example. Like everything Siemens, there's 1,000 different ways to do it, and they all work. But I'll show you one way, maybe give you a few hints the way you like to do things. Okay, so I was going to show the CU. Uh, really, this programs, like the drives do. It's just one of those things that sometimes I see no one actually puts a communication block to talk to the CU itself. And sometimes it can actually have a few interesting things in there that you might want to know about. Let me actually pull up the CU communications there. There we go. You can get its fault code and its alarm code. It's probably and if the status word here, so it can tell you, um, if it's upset about something and what is it upset about. And I gotta go to there we go, the binary connector. Wait a second. Okay, so that's the one I want. Okay, here's word 2. I have set up to actually give us a status of all the digital I/O, and that can be useful if you want to do code manipulation with uh, data coming into uh, an I/O point on the CU itself for monitoring, or just using that I/O for uh, general purpose I/O instead of buying more PLC I/O. Uh, Now, of course, if you're doing the DCC charts, you can only have one DCC chart per software object. So if you want to divide the load out for like something you're doing, you can have one in the drive, one in the other drive, the next drive, how many ever drives you have. You can also put a chart in the CU object, so that gives you a place to put another independent control chart, and then you can have the data coming in and out. But what I got here is just a basic free block type setup based on actually the two-word one. So you select two words first, right, and then you select, after you select two words, then you select free telegram if you're going to do something customized. The reason you do that is so that all the basic routing and stuff is automatically set, and you don't have to go manually set it. So, when you look here, it's like these are just all the default uh, bits, right? And I didn't have to set those. So that just kind of quickens up the whole process. So, and here's the status word. Uh, and so I picked 4 words. When I set this drive up, let me get to the hardware. Get to the drive. I set that guy up. I picked a 4-word telegram. There we go. Something I did here. You got to change the names offline, but instead of just having the telegram type descriptor show up here, in offline mode, you can actually change this name. And when I was setting stuff up, I inadvertently actually picked the hardware address of the slave. The slave is not the CU, but what you get by default is this sort of descriptors, and it doesn't really tell you what that telegram is talking to. So I went over here and put my common names that I would call the devices, the CU, the TM31, the drive 1, drive 2. So I changed those names from the telegram type to something that means something for me. So it actually shows up over here, right here. So it makes life a lot easier when you use some uh, common names. And let's see here, go to properties, and there's that hardware identifier, that critical for any of the communication block stuff, and it's 278. Of course, I had accidentally clicked on the slave, and I got 277. Well, of course, comm blocks don't work when you put the wrong hardware address in. So here I wrote a little basic little block. There's that hardware address that's so important. And one of the things is it's got a little alarm coming out. And if you look at the drive itself, there's that alarm, 50,005 and 50,005. And the reason I have that alarm is because I have an extra COM board. This is a Profi Bus CU, but I have the Profinet card in there option, but it's not hooked to anything or configured. So it's just warning me that it's there, not doing anything, no big deal. But it does show you it's nice because it shows you that there's the alarm, and then the alarm shows up here. Um, now I didn't put a variable here, right? I could put a bool here, and this would be on. So if I go to the actual little block that I wrote, go online, and there we go. So you can see that status bit is showing yes, I am in alarm. There's a little data structure. This data structure I'm pushing the data into. This is not a real big data structure, and it's working good for me. Previous video I was doing a little motion thing. I think I had my data structure a little hosed up. Didn't like me pushing all the data directly into it. I think actually the data structure was slightly the wrong size or something. But this one's right. So here's the meat of this little block. First thing I got to do is, the hardware address gets pushed in. Now notice the hardware address here is showing up in the hexadecimal format. So it's 116. I probably can change the display. There we go. There we go. So it's 278, right? Like we're pushing in. It's just this temporary variable inside the block, just for some reason, shows up as base 16 hex. And so like this DP read that you use for talking to any of these type of devices for data transfer. Here's its address. It actually, because that pointer points to how many words I picked, so it already knows how many words it's going to move in. And it is working correctly because I don't have any code. You'll get something like 8092 is usually the most common one. Usually it means you got the wrong hardware address set. Or you're pointing to the wrong device, right? And you're pointing to its address, and it was a different number of words. And so you'll get in hex, you'll see 8093. Or not? Is that in hex? Yeah. So you'll see that. But if you double click on this bad boy, will it open up? Oh, maybe because I'm online. Wait a second. F1. There we go. F1. Get the help up. I've shown this in other videos. It gives you the little translation of what those codes mean. Alright, there we go. Turn it back on. So, there we go. So basically I'm pushing those 4 words, reading them from the drive, comes in, shows up in this little data structure. This data structure is just to make my life easy. Go over here. Let's see. Here's the data structure. So in the data structure, I got the status is coming, the command word's going. Uh, this is where I set the acknowledge bit going out. You got to remember when you set up these data structures that you're doing 2 bytes in a word. High byte first. So this is the high byte. It's first. Low byte last. This is the low byte. So it's kind of non-intuitive because when you look at it as a word, it's like it's kind of looks like it's bass axe word there, but that's what it is. Um, so just be aware of that as well. Um, and then for the statuses, I'm sending uh, the default status, the alarm status, and the status of the bits themselves that go to the I/O that's directly built in. Uh, this I/O is actually, now you say, hey, you've been talking about the bytes are swapped. Yeah, the kind of the default way the drive sets up this, it actually flips the bytes so they're backwards in the drive, so they show up in the PLC this way, which is more intuitive. Um, so it's just another little gotcha. Just be careful about that and double check that you set the drive up that way, and that this matches the way they come from the drive. In fact, let's go look at that. Ba, 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 ba. So let's see. There we go. I can't see them real well because the descriptions kind of run off, but you can kind of see from the addresses, see how they've actually put the low byte of all the addresses here second and the highs first, so that then they show up over here um, the way you would kind of expect them to show up, right? So again, it's just something to always kind of be cognizant of if when you're doing this type of high byte, low byte thing stuck in a word, which way the bits are actually going to show up. When I first started, I actually sometimes this was a little hard to make sure I gripped it in my brain. I'd actually just hardwire the first one on and see where it showed up. But it's you guys are smarter than me. You probably don't have to do silly things like that. But so that's just a little data structure that I'm pushing this into. So all the data actually then shows up with the names that come from the data structure, which are the names that mean something from the drive, instead of just bit 0, bit 1, bit 2, which is hard, especially for someone coming behind you to figure out. And even like for me, 6 months later, I'll come back and I'm like, I don't remember what bit 1 was or bit 0. I didn't give it a name. So there you see the data structure. I named it alarm and pushed it out of the block. I give it a little on the output of the block itself. We just push it out. Then I can reset faults from the block, so it comes into the block and then goes out through the communications and acknowledges the fault in the CU. This is something that's not standard in Telegram. That was actually added. This is if you have a line module, which you've got to have some sort of line module to actually make it go. It's meant to start the line module up. I think I got that pointed wrong. I have it pointed to the wrong bit there, but I don't actually have a line module. I have a 650 volt power supply in my lab, DC power supply that I built that made to charge up these drives. Oh, and here's something else I actually forgot about until I got the high alarm, It used to be alarm numbers were below 32,000, so you never had to worry about this. But in the newer Sinamics, I guess not that new anymore. Dating myself, the last 10 years, they have numbers that range, up into the 50,000s. Well, what happens when you look at an integer above 32,000? Well, if it's a normal integer, what you see is a negative number right there, because the 15th bit, or the last bit, however you want to count, 15 or 16, but the last bit is the sign. So if it's a 1, it's a negative number. If it's a 0, it's a positive number. So you get this. You're like, well, that number doesn't match what the drive says at all, right? It's like, well, this thing says 50,005, and this says minus 15,000. Wow, that's crazy. Well, what you got to do is you got to either you can define it in the data structure, which probably I should change the data structure just to make stuff look good as well, to be an unsigned int. That means all 16 bits are used to display the number, and then it'll show up as 50,005, like it should. So I actually quickly had changed that there, and then I changed it in the main for the little temp words I push it into for visualization. I changed that to an unsigned integer as well, so it shows up there, and kind of makes sense. Normally on these blocks that we write here, we actually bring out the DP read and write status, so we can see if we're pointing to the wrong address. So that's just something you can do or not do. See, sometimes people just put just a bit that comes out and says, Comm read problem, and back in the block they just look for anything non-zero. Either the read or the write is non-zero. It just says, hey, there's something wrong. And 99, especially now in Portal, there's a lot fewer issues that can give you that. So 99% of the time, it's you accidentally pointed it to the wrong thing here, right? Because if I had pointed it to this address, I'd be, and then try to push it into a data structure of basically 4 words. These are 12, and of course it'd blow up and give you an error on that read write as well. Even though it's a valid hardware address, it's not the valid data structure length. So anyway, as you can see, that's just like any of the other ones that I was talking about, how you read and write data to a someplace right. Yeah, and here's the write, where I'm writing the data back out that I wanted to send to the drive. So it's just like any of the other devices, but it can be kind of helpful to at least have, like this one, just real basic, where it tells you if there's an alarm or a fault on the CU. I haven't done the same, and normally we do have one for the TM31 as well, that I haven't popped it in this project. So it as well will give you faults and alarms, and it's a semi-intelligent device, so it can be good to get that data out. At least you can get it out as a a bit or something to flag the operator that there's a fault on the I/O device, and that can be pretty critical, especially during when he's calling for maintenance. He can say, hey, it's saying that the I/O module X has some sort of fault on it, and obviously if it's got important I/O, the line's not going to run or run right, and lead them right to the problem. So you can get as fancy as you want. We've actually used these then where all the I/O data actually comes out of the block, so you can see each point individually as a bool. We make inputs for the I/O if we configure them as digital outputs from the CU, so you can actually control them as outputs right from your program. So the sky's the limit. with Siemens configuration. So hopefully this is a few little tips. Uh, so good luck.